Alright everybody, welcome to Passionate Minds. My name is Prabhasha, and today I'm going to be teaching to you a little bit about SCH3U, grade 11 Chem, and today's lecture is going to be focusing on moles and definite proportions. Alright, so to introduce the subject of moles, or MOL as a scientific unit, they are a scientific unit that's used to measure out large quantities of small particles. So labs tend to use a large amount of quantity of very, very small particles. So it's pretty much impractical to say that we're using 900,000 particles of carbon, for example, which is a lot smaller than the actual number of particles that are used within lab experiments. But just referring to each particle individually is very impractical because there's such a large amount of particles that are being used. And because the atoms are much too prevalent and small to count individually, we're going to be using moles to group a large amount of quantity of them together to understand what's happening a lot easier. So, a mole is 6.02 times 10 to the 23rd particles. When dealing with experimental data, we're going to get a large quantity of particles, and it's much easier to group them into moles than it is counting individual particles. Because if we look at this number, 6.02 times 10 to the 23rd, that's an extremely large number. Take into consideration, all the grains of sand on Earth total about 7.5 times 10 to the 18 grains. This is not even close to a mole. For another reference, there's 4.7 times 10 to the 20 particles of water on Earth, about 1% of a mole. And the number of particles in a mole is based off the number of atoms in 12 grams of carbon-12, discovered by a scientist by the name of Avogadro. This number, 6.02 times 10 to the 23rd, is also more commonly referred to as Avogadro's number. So, large N, capital N, subscript A is referred to as Avogadro's number, 6.02 times 10 to the 23rd. The general unit for this number right here is particles per mole. However, this can be substituted for compounds per mole, molecules per mole, atoms per mole, whatever the question at hand needs. We'll be going into this a lot more later on within a lot of examples. Small n refers to the number of moles in a substance, and this unit is simply mole. Large N indicates the number of particles within a substance. So, this can tell you the number of atoms, ions, or molecules, units, that are present in 1 mole of a substance, and the unit is usually particles, but this can also change depending on what we're looking at. It can also be ions, it can be molecules, it can be whatever the question at hand has. And whatever this unit is going to be what NA's unit is also going to be per mole. And again, we'll take a look into this more later on. So, looking at the simple equation, moles, Avogadro number, and the number of particles, N equals big N over NA. The number of moles equals the number of particles divided by 6.02 times 10 to the 23rd particles per mole. It's important to understand that Na is going to be a constant within every single equation in question. This Na will never change. What will change is the number of moles you have and the number of particles, ions, molecules that you have. So, taking a look at an example, 1 mole of carbon. This is very simple. 1 mole is going to be the number of particles divided by 6.02 times 10 to the 23rd particles per mole. We multiply 6.02 by 1, and we get 6.02 times 10 to the 23rd particles, which equals the number of particles in 1 mole of carbon, as indicated here. Now, 1 mole of hydrogen chloride, hydrochloric acid. 1 mole is going to be the number of compounds in this question, because hydrochloric acid is a compound, not just a regular particle, divided by 6.02 times 10 to the 23rd compounds per mole. We multiply this by 1, we get 6.02 times 10 to the 23rd. So we have that many units of HCl in 1 mole. And since HCl has 1 atom of hydrogen and 1 atom of chlorine, we're going to have 6.02 times 10 to the 23rd atoms of hydrogen and 6.02 times 10 to the 23rd atoms of chlorine in 1 mole of HCl. If we had two atoms of hydrogen or two atoms of chlorine, this number here would be different, and I'm going to be showing you examples of this a little later on. All right, so a bunch more examples. This is an equation we're going to need to know throughout all the examples. This can be rearranged if we're looking for the number of particles instead of the number of moles, as we're going to see right here. So 2 moles of lithium chloride. 2 moles is going to be the number of particles of LiCl divided by 6.02 times 10 to the 23rd. Multiply these two together, you get 1.20 times 10 to the 24 particles of LiCl. And since there's only one atom of lithium and one atom of chlorine, we're going to get 1.20 times 10 to the 24 atoms of lithium and 1.20 times 10 to the 24 atoms of chlorine in 2 moles of LiCl. Now, looking at this right here, 0.5 moles of MgCl2. 0.5 moles is going to be N divided by 6.02 times 10 to the 23rd. Multiply these two together, you get 3.01 times 10 to the 23rd particles of MgCl2 present. However, since there's 2 atoms of chlorine present in MgCl2, we're going to be multiplying the number of atoms of MgCl2 by 2 to get the number of atoms of chlorine within this molecule. So we're going to have 6.02 times 10 to the 23rd atoms of chlorine, and we're going to have 3.01 times 10 to the 23rd atoms of magnesium in MgCl2 within a quantity of 0.5 moles. All right, another example, 0.75 moles of aluminum chloride. So, as before, 0.75 moles is going to be N over Na, which is 6.02 times 10 to the 23rd. Multiply these two together, you get 4.52 times 10 to the 23rd, which is going to be the number of particles of AlCl3. And since there are 3 atoms of chlorine present in AlCl3, we're going to be multiplying 4.52 times 10 to the 23rd by 3, and we get 1.35 times 10 to the 24 atoms of chlorine. And since there's only one atom of aluminum, this number is going to be the number of aluminum atoms present in AlCl3 within 0.75 moles. All right, now looking at a little bit different question. How many molecules of water are going to be present in 1.08 moles? This is simply 1.08 moles is going to be N over Na, and we're going to be doing the same thing. Multiply these two together. 6.50 times 10 to the 23rd particles is going to equal to N, and this is how many molecules of water are present in 1.08 moles of H2O. And to get the number of atoms of hydrogen, if we wanted to look at that, just multiply 6.50 times 10 to the 23rd by 2, and we're going to get, I believe, 1.30 times 10 to the 24th. But we're going to have only one atom of oxygen, so it's going to be 6.50 times 10 to the 23rd atoms of oxygen. Now, this question right here, we're looking at the number of moles present in 7.81 times 10 to the 25 molecules of HCl. So a little bit different than what we were doing before. Using the equation that we already know, N equals big N over Na, we simply have to divide the number of particles divided by the Avogadro's number. So 7.81 times 10 to the 25 divided by 6.02 times 10 to the 23rd. This is going to be particles. This is going to be particles per mole. As units cancel out, we're going to have moles on top, which is going to give you 1.30 times 10 to the 2 moles, or 130 moles. And just taking a look at the significant digits we have present within these examples, you might notice how I'm doing it incorrectly, and you'd be right. For example, 2 moles should be 2.00 moles, 0.5 should be 0.500, and 0.75 should be 0.750. The reason I'm not doing this here is just for simplicity's sake. I'm only looking at the sig digs present in the number of particles, but for the other examples, just make sure to have the right significant digits, and it should be 0.500. This is going to have 3 significant digits because some 0.81 times 10 to the 25 has 3 sig digs, and 6.02 always is going to have 3. But just for simplicity's sake, in these examples, I have 3 significant digits present with every example. And yeah, just taking a look at the final example we have, how many moles of H2S are present in 9.23 times 10 to the 20 molecules of H2S, and it's going to be 9.23 times 10 to the 20 divided by Na, 6.02 times 10 to the 23rd. We're going to get 1.53 times 10 to the negative third moles. This is going to be particles. This is going to be particles per mole. This is why this is going to equal to moles. And 1.53 times 10 to the negative third is also equal to 0.00153 moles. All right, now taking a look at molar mass. Molar mass is the mass of 1 mole of a particular compound or substance. Now, mass is always going to be measured in grams, and if it isn't, you're going to want to convert to grams, because molar mass is always going to be measured in grams per mole, as indicated by the unit here. For example, if you have the mass in kilograms, you should know that 1 gram is equal to 1/1000th of a kilogram, or 1,000 grams is equal to 1 kilogram. So if you have a kilogram, you're going to want to multiply that number by 1,000 to convert it to grams. Likewise, if you have a milligram instead of a gram, you should know that 1,000 milligrams equals 1 gram. So you're going to want to multiply that number by 1/1000, or 0.0001, to get the number of grams within that particular substance. The symbol for molar mass is going to be a big M, and again, the unit's just going to be grams per mole. Now, the molar mass of a particular substance is going to be equal to its atomic mass, which is already found on the periodic table. So, for example, we're going to look at a couple more examples later on, but sodium has an atomic mass of 23.0, which means that its molar mass is also going to be 23.0 grams per mole. Like the atomic mass, the molar mass will be different for every single element. This is why 1 mole of hydrogen is going to be less in mass than 1 mole of carbon. Moles count the number of particles present for a particular substance, whereas the molar mass represents the mass of a particular substance of 1 mole. For example, if you had 5 Big Macs and 5 Junior Chickens, it's obvious that 5 Big Macs would weigh more. Likewise, if you had 5 moles of carbon and 5 moles of hydrogen, 5 moles of carbon are going to weigh more because it has a higher molar mass than hydrogen does. Now, just taking a look at the periodic table, we can see the atomic masses at the bottom. Hydrogen has about 1.01, sodium has about 23.0, magnesium about 24.3, calcium about 40.1, potassium about 39.1. I'm rounding here. But those numbers right there are going to be equal to the molar mass of those particular elements as well. And that goes for all the elements in the periodic table. Now, taking a look at the molar mass of compounds, the molar mass of a compound is obtained by adding up the molar masses of the atoms present and multiplying them by however many atoms are present for one particular compound. For example, these are just 2 quick examples. I'm going to be diving deeper into this later on. Taking a look at water. Water has 2 atoms of hydrogen and 1 atom of oxygen. 2 atoms of hydrogen, to get the molar mass of hydrogen here, we multiply the molar mass of hydrogen by 2 because there's 2 atoms present, and we get 2.02 grams per mole. There's only 1 atom of oxygen, so we multiply the molar mass of oxygen by 1 to get 16.00 grams per mole. And to get the molar mass of the entire compound, what we do is we add up the 2 atoms that are present. So we add up, the 2 elements that are present. So we add up 16.00 by 2.02 because it's 2 atoms of hydrogen and only 1 atom of oxygen. We get 18.02 grams per mole. Taking a look at another example, aluminum chloride. We have 1 atom of aluminum, which is going to give you 27.0 grams per mole. And we have 3 atoms of chlorine, so we're going to take chlorine's molar mass, 35.45, multiply this by 3, and we get about 106.4 after rounding. Adding these 2 numbers together to get the total molar mass of aluminum chloride, we get 1.06.4 plus 27.0, and we get 133.4 grams per mole. also indicated by 133.4 m. Now taking a look at some simple examples, again, the equation for this is the number of moles is going to be equal to the mass divided by the molar mass. Also, if we rearrange this, the mass is going to be equal to the number of moles multiplied by the molar mass. Again, moles is going to be mass in grams divided by grams per mole, the molar mass. These two examples, after taking a quick look, how many moles are present in 7.23 grams of magnesium chloride? So the molar mass of magnesium chloride is what we need to find first. To get this, we take the molar mass of magnesium multiplied by 1 because there's only one atom of magnesium, and then take the molar mass of chlorine multiplied by 2 because it's two atoms of chlorine, and we get 95.2 grams per mole. So N is equal to M over big M, which is going to be 7.23 grams as indicated in the question here, divided by the molar mass, 95.2, and we get 0.0759 moles. Also, we can write this out as 7.59 times 10 to the negative 2 moles, just to make this a bit easier to look at. Looking at the mass of 19.7 moles of silver nitrate, the molar mass of silver nitrate is going to be 1 multiplied by the molar mass of silver, 107.9, and then we add the molar mass of nitrogen multiplied by 1 because there's only one atom of nitrogen, and then we add the molar mass of oxygen, but we multiplied this by 3 because we have 3 atoms of oxygen present in the compound of silver nitrate. Adding these three together, we get 169.9 grams per mole. Again, the equation is N is equal to M over big M, but since we're looking for the mass, we're going to rearrange this, so M is going to be equal to N multiplied by big M. The mass is going to be equal to the number of moles, 19.7 indicated here, multiplied by the molar mass, 169.9 grams per mole. After multiplying these two together, we cross out the moles, we get 3,347 grams. Rounding these to the correct significant digits 3, because we have 3 significant digits for the moles here, we're going to get 3.35 times 10 to the 3 grams, or 3,350 grams. Alright, taking a look at a couple more examples, let's take a look at the first one right here. How many moles are present in 25.3 grams of C6H12O6, also known as glucose? To find this answer, we have to find the molar mass of glucose, which is going to be 6 multiplied by the molar mass of carbon, which is 12.0, plus 12 multiplied by the molar mass of hydrogen, 1.01, and 6 multiplied by the molar mass of oxygen, about 16.0, and we get 180.1 grams per mole. Now, N is going to be equal to the mass divided by the molar mass. Take 25.3 grams divided by 180.1 grams per mole. The grams cancel out, mole goes on top, and we get 0.140 moles of glucose in 25.3 grams of it. Now, taking a look at how many grams are present in 0.00913 moles of hydrogen chloride. Now, the molar mass of hydrogen chloride is going to be 1 multiplied by the molar mass of hydrogen, which is about 1.01. Then you add 1 multiplied by the molar mass of chlorine, which is about 35.45, and you get about 36.5 grams per mole. Now, the equation is N is equal to the mass divided by the molar mass. We rearrange to isolate the mass, so M is going to be equal to the number of moles multiplied by the molar mass, which is going to be 9.13 times 10 to the negative third moles multiplied by 36.5 grams per mole, and we get about 0.333 grams, which is also equivalent to 3.33 times 10 to the negative 1 grams. Now, the third example we have, how many moles are going to be present in 0.000278 grams of calcium carbonate? So, the molar mass of calcium carbonate is going to be 1 multiplied by the molar mass of calcium, which is 40.1. Then we add the molar mass of carbon multiplied by 1 because there's one atom of carbon, and we add the molar mass of oxygen multiplied by 3 because there's 3 atoms of oxygen in calcium carbonate, and we get about 100.1 grams per mole. Now, the equation again is n is equal to m over big M. N is going to be equal to 2.78 times 10 to the negative 4 grams divided by 100.1 grams per mole, and we get 2.78 times 10 to the negative 6 moles present in 0.00278 grams of calcium carbonate, a very small number of moles. Final example we have, how many grams are going to be present in 7.93 times 10 to the 4 moles of hydrogen sulfate. Sulfuric acid as well is another way to indicate this. The molar mass is going to be 2 multiplied by 1.01 to indicate the number of hydrogen atoms present. And then we add 1 multiplied by 32.1 to indicate the number of sulfur atoms present, and then we take 16.0 multiplied by 4 to indicate the number of oxygen atoms present to give us a total number of 98.1 grams per mole for this particular compound. So the equation is n is equal to m over m. We rearrange because we're looking for the mass, so m is going to be equal to n times big M. N is going to be equal to 7.93 times 10 to the 4 moles multiplied by 98.1 grams per mole, and we get the mass is equal to 7.78 times 10 to the 6 grams. Finally, these are a little bit longer questions. We're going to be incorporating everything we've learned today. So, how many atoms of chlorine are present in 9.97 grams of carbon tetrachloride? How many grams of chlorine are present in carbon tetrachloride? So, first things first, we need to find the molar mass of this particular compound. So we take the number of carbon atoms present multiplied by the molar mass, and we take the number of chlorine atoms present multiplied by the molar mass. So chlorine, we get 149.8 grams per mole as molar mass of this compound. N is going to be equal to m divided by big M. We need to find the number of moles before we can find the number of atoms. N is going to be equal to the mass divided by the molar mass, and we get 6.66 times 10 to the negative 2 moles. Now, to get the number of atoms of chlorine present, we have to use the equation we learned before. N is equal to big N over NA, and NA is always going to be a constant, so we can just plug in the numbers that we already have. So, rearrange to find the number of particles present. N times NA is going to be big N. 6.66 times 10 to the negative 2 moles is multiplied by Avogadro's number is going to be big N, and this gives us 4.01 times 10 to the 22 particles equivalent to N. The number of particles of carbon tetrachloride, CCl4. However, we are looking for the number of atoms of chlorine present, not the number of carbon tetrachlorides present. Because of this, we're going to take the number of carbon tetrachlorides present, multiply it by 4 because we have 4 atoms of chlorine for every particle of carbon tetrachloride, and we get 1.60 times 10 to the 23 atoms of chlorine and 9.97 grams of carbon tetrachloride. Again, a different question where we go the different way. How many grams is present in 1.93 times 10 to the 25 particles of sodium hydroxide? So we have the number of particles of sodium hydroxide. We have the Avogadro's number. So we're just going to find the number of moles present. N is going to be big N over NA. We plug the two numbers we already have in. Particles cancels out, and we get 3.21 times 10 to the 1 moles, or 32.1 moles. Now we have to find the molar mass of this particular substance. We multiply 23.0 times 1 because there's 1 atom of sodium, 16.0 times 1 because it's 1 atom of oxygen, and 1.01 because there's 1 atom of hydrogen. We get 40.1 grams per mole. And then we take the moles that we already have. N is equal to m over big M. Rearrange to isolate m. M is going to be equal to n times big M. M is going to be equal to 3.21 times 10 to the 1 moles multiplied by the molar mass, which gives us 1.29 times 10 to the 4 grams of sodium hydroxide that are present in 1.93 times 10 to the 25 particles of sodium hydroxide. And that does it for today's lecture. To learn and understand more about moles, molar mass, and the number of particles and all these proportions, the best way to learn this particular these particular what am I looking for? These particular ideas and just the best way to learn in this particular area is to practice a lot of different types of problems. Just keep doing different types of problems where you either have to find the number of atoms present, number of grams present, whatever you're looking for. Just keep on practicing, and this will help you understand this particular subject more. And that does it for today. Thanks for listening.